right,
Hey.
Sebastian.
Simon.
Thanks for taking your time
Sure.
here in Kirspe at Impulse,
Okay.
showing me around and also having the opportunity to discuss the innovation Impulse delivers here on the podcast. Before we jump into today's discussion on magnetization equipment, I want to understand how you and Impulse found into e-mobility.
E-mobility. Well, the magnets have been there before e-mobility, and we find magnets absolutely attracting. So where the magnets are, there are we. We have to magnetize them. We have to activate them. And so the market has developed for the e-mobility, and there came we into this game. It's absolutely interesting. Anything with electric motors is interesting for us. There are magnets. But also, of course, the green energy is a very interesting field to work in.
So just historically speaking, because the e-mobility landscapes is around for, let's say, a decade, roughly, right?
Right.
What did you do before? So where did your competence come from?
Well, the e-mobility is that old, maybe partly, but the use of rare earth magnet came up in the 80s. I started my business in the 90s. I started to operate in that field in the 90s.
Yeah.
That was my start, right, with magnetizers.
Okay. Wow.
Yeah. Already there have been rare earth magnets. Neodymium have been widening up, have been exploring the market very widely.
Okay. Specifically for e-motors all the time, or were there also other
There are other
magnetization?
applications for sensors, for loudspeakers, for many other things that contain magnets. But still, yes, motors is the biggest field, have ever been the biggest field. Yeah.
And are increasingly the biggest field, or would you say because there are also other alternatives to permanent magnet excited motors, that the use of magnets will be lower in the future?
That is
That's
always
a critical question, I know.
a good question, whether this becomes a disruption or not. That maybe other electric excited magnets, rotors can be used or can be applied in a manner that magnets become obsolete and can be replaced by that. It is not to be foreseen, and in the past 4 decades that I can observe, the use of magnet has been exploding, and it is not to be finished, not by far. We expect growth of the electric of the EV market in the magnets still by 8 times to 10 times within the next 10 to 15 years.
So not e-mobility per se, but also e-mobility and permanent
yes,
excited
also the permanent magnetic
motors.
Yes.
Okay. Wow.
Yeah. They will not be replaced fully. However, the share of, let's say, reluctance motors may increase, but the permanent magnets cannot be taken out of the game.
Yeah, maybe you can elaborate us really quick on why and what are the performance metrics you can gain or get with permanently excited motors, magnets in a motor, and other solutions that are out there.
Yeah.
So just give us an overview of what is existent, where magnets come into play, and then we segue over and discuss what Impulse is doing in order to promote the innovation of magnets and motors.
Well, the permanent magnetic motors are incomprehensible in terms of size and power density. They cannot be coped. They cannot be achieved with electrically excited rotors. They cannot be approached by reluctance motors. There will always be more mass, more length, more size by these motors. The question still is that a problem if they are bigger? They are cheaper, likely. They are louder, in the sound. They are louder, likely. They produce more heat.
So less efficient.
Yeah, less efficient. So these are the problems, and when you try to fight the last per mil in efficiency, the permanent magnet will always make the difference.
And also in power density, as you explained. Okay, I understand. So what does Impulse deliver? What's your key competence for building up new or developing new type of motors.
If you try to assemble a motor with permanent magnets, you will easily find out that it's much easier to assemble it in a non-magnetized way. And so it needs something that you can assemble it without magnetization. Then you take the fully assembled rotor into something which we build and deliver, which will energize the magnet and create a magnetic field to magnetize into saturation. So by the geometry of the rotor, we define a certain flux or magnetic flux shape in our magnetizing coils that will be able to magnetize 100% of the magnets.
From an industrial perspective, so you're magnetizing the rotor prior assembly or after assembly?
After assembly.
After assembly.
This is the goal, always.
So this is important to note, right? That everyone gets that. So you magnetize the rotor, and then you bring together, like in the assembly street,
only very rare cases where this is possible to magnetize through the stator.
Mostly I was wondering like where this would work.
But this is in 2-pole ferrite motors, for instance.
Good.
Some are 4-pole as well, but that's possible. But
I mean, So I got you. So your key competence lies in magnetization of rotors, and then for different geometries.
Absolutely.
You have radial motors, but you also have axial motors, as I was also able to see. And we have one demonstrator with us now where we can see the tool that you use for the magnetization. Can you explain us how this works in general? So we understand we have the stator, we have the rotor, right? Those two components are needed to generate the torque in order to propel the vehicle forward.
Absolutely.
So let's jump into the rotor and how it works, because then we better understand your job and the competence you bring in. So let's have a little physics class on magnets and how they work.
Are you ready for that?
Well, I don't know.
I brought you some pictures. I'm scrolling through some of those, and I want to bring you into a slide which is showing a part of the hysteresis loop of permanent magnets. And I don't know if you have heard, I'm sure you have heard about hysteresis loop, if the audience has heard about it, but you know all the hysteresis which is going in a certain loop up and down.
What does hysteresis mean in this regard?
Hysteresis means you have multi-statuses. You can have a status which is a firm status anywhere within the loop. That is a status of the permanent magnet. It can be magnetized to fit on this point or on that point, and it is kind of stable there.
So on the x-axis here we have the magnetization of the magnetic material.
This is the field strength you apply. Whenever you apply a field strength, the magnet will react in its magnetization. So normally if you apply a positive, then the magnetization goes up positive. Then
outside of the screen right now.
Outside of the screen. Then you return back to the zero and it stays somewhere here. If you shoot over into the negative, it remains stable until a certain point. We call it the knee point, and it collapses, passes through zero, and then we can mirror the whole loop into the negative.
Okay, but to explain this in layman's words, because I'm a battery researcher and you really have to be careful not to leave me behind. This is the positive magnetization area, the excitation, so to speak, right? So when I have a piece of battery material, of magnet, and I apply this field to this magnet, then it will be polarized in the direction that I apply this field strength to. And there's a maximum that I can reach, right? That's this line. And if you push further on this, like depending on where you go, how far you go, you will be on one of those equilibrium lines later on. Meaning, when I have excited this material, I'm on, let's say I did a good job and I applied a really high field strength to it, then I'm on this line. Which means that when I later load the motor, like put a force on this magnet because I'm pushing down the gas pedal or the electricity pedal, then
you go in that direction.
We are pushing in this direction, and the magnet has withstand this force.
Yeah.
Right. And it can go all the way up to here, and at some point you will lose the magnetization again.
Yeah.
Correct?
Absolutely.
So the goal is, I think, if you go one slide further, then I can put it in my words. At this point, and you can take over now again. If I'm at this point and I would go further, I would lose the magnetization of my motor.
Yeah.
So I would basically break the motor. Correct?
Yeah, it is a destruction of the motor because the magnets will be reversed magnetized or collapsed.
Yeah.
Its magnetization.
So the motor would be damaged.
You have to disassemble the rotor and bring it back into first the thermal chamber and then into the magnetization.
Yes.
Then you can reassemble, but it's like spoiled.
Yes. Yeah. So why is there the 70% mark then?
We have to to define what we need to do, what our task really is what do we need and what do we understand under saturation of a magnet.
Yeah.
It is easy to understand. If I go to infinite into that direction, I will be on the outest loop in the reverse until we cross here H6J. If I only go to 400, I will collapse this in this line in the negative way. If I go to 460, I will take this path. If I go to 700 here, I am almost here. But then we call it a gray zone. Here is what is very interesting for us, because I can go back a few slides before. There are some reports, technical reports, been written, which define what is saturation, and
So in layman terms, saturation
is... In layman terms, I have a very good equivalent. If you have a glass, you can fill it up with water. When is the glass full? When it's full. So you can pour more water, it will not be fuller.
Same for saturation of a magnet, right?
And the same for the saturation of the magnet.
So in an analogy, the saturation is equivalent to the force that you can excite, or the excitement of a magnet, and then the maximum force that this magnet can then exhibit onto a polarized other material.
Yes. That is the maximum use of it. And in order to achieve this fullness of a glass of water, this says we need a certain amount, and then they put a factor 2. It's like filling up the water, and then you pull more because you might shake something.
Yes.
There are physical reasons for that, which are well investigated.
A little bit more of what? That's my question.
Of field strength. Of the vertical.
Which correlates with amperes, right?
Yeah. So this, what they claim to have, the 2268 kiloamps per meter, is a weird unit. Ampere per meter is something about magnetic field strength.
Yeah, but that's the density of like the amperage density, linearly speaking, that I need in order to polarize the magnetic material.
Correct.
Until saturation. So when the water, the glass of water is full.
Yeah, correct.
Okay,
and
gotcha.
If you take this into your mind, 2268, and we go back to this, we see the assembly of these curves, and we see 1600 is here pointed as the outest part of fully saturated.
Gotcha.
Which is well developed by vacuum smelter in this case. But we have also research on other brands or other types of these neodymium iron boron magnets. They all behave very similar. So 1600 is about the value that would be sufficient. And it shows the technical report prescribes us 2268. We have to take the square of the ratio to understand what the energy we need to provide to the magnetizing coil in order to establish the field, the magnetizing field on this horizontal. So if we take the square, we have the energy that we pump into the coil. And a difference of 2300 over 1600 is huge. It's like a factor of 2.5. It would make us it would mean that we cannot magnetize like 50% of the motors in the market.
One short comment. Don't look into the camera. Okay. Like we will cut it out, but that doesn't. Yeah. We just here.
Sure. Okay. I understand. So we must understand that there needs to be a gray zone that we need to consider from maybe 2200, but also down to 700, to understand where are regions in magnets that may be not fully saturated, physically speaking, in total whatever.
Because the energy that you have to apply to those magnets is sometimes not physically possible. In the geometry that you locate the magnets in the rotor.
Correct.
Or it's just not economical to saturate it all the way through, right?
I would say in 90% it's not economical, but there are cases that it's physically not possible because of the arrangement is topology which doesn't work out.
Understand. Okay.
Okay, now to show this 70% line, a designer of a rotor will never approach the knee point in the working point. So the magnet will be loaded by the stator field, which is always reverse, and the stator field will in the knee point demagnetize the magnet. You can lose magnetization and spoil the rotor by that. So he will always have working points in a region around 70% of the knee point, not far beyond. But if we take this as a working point line, we can say 100% is right here, and if we have a magnetization of 720%, we are right here on that point, maybe with 90% of the magnetization. And by this, we can define a result of the magnetization that we provide. And since we are talking economically, our customers are interested in what is the result we have and what is the money that we invest. So this is our duty to make it transparent.
Yeah. So to summarize this, you are dealing with the physics of magnetization of magnets, obviously, to magnetize rotors that will then provide the torque for the motor later on. Okay.
Yeah.
So how does it look like? So how do I build those machines to magnetize rotors? Can you just explain a little bit your work and in this regard?
The magnetizing machines are more or less capacitor discharge. We charge up capacitors up to voltages of 3000 volt or even more, and then they will be triggered, the discharge, through a semiconductor and discharge along the magnetizing coil. And by this we have the optimum is a nicely short pulse.
Yes.
And a very high current.
Yeah, can you show? You have, I think, a good picture of this that we can have a look at that. Yeah, exactly.
I can show you here. This is the magnetizing coil with a plus conductor, a minus conductor, and inside you see the location of permanent magnet in the rotor. This is a V-shaped rotor, and the flux lines can be also observed here. They pass through the magnets, and our task is to create field strengths strong enough to saturate those magnets.
So the field lines, you have the different opposing poles, and then of course due to that the field lines are running around those magnets in circular pattern. And what you're trying to do is to let the field lines run through the magnet in order to polarize the magnet. So it's important that you orient your, do we call them electrodes? I don't know. Your magnetization electrodes in a way that they coincide with the desired direction of the magnet in order to be magnetized.
Electron spins in the magnet.
Yeah. Okay. No, electrodes. I mean, I called these electrodes right now.
The conductors.
Conductors.
Just
Okay.
call them conductors.
Yeah. Okay.
You can see this would be a magnetizing coil. The rotor will be pulled in, and then the coil is like a stator all around the rotor. So then there will be different shapes available in the traction market. In the e-mobility, they develop different styles of or patterns of the magnets. Like you see these here, they are mostly used for hybrid motors with a high number of poles, or you can have other straight lines. And there are many others, like a U shape. We call this because it's like a U.
And every topology has different torque characteristics, or why would you want to have different shapes of magnet placement?
In the first approach, you want to have a high use of the magnet. So you might be wanting to bring in a lot of permanent magnets and still have the effect. So you may double the lines. You may go deeper. If you have only a surface magnet, you can bring in more magnet material in the U shape.
Okay.
But still, there will always be in this or that, and this or that, will be a reluctance moment that is created by the steel path, which is going from here to here.
Between the magnets.
And this creates an additional torque which can be used. It's kind of a hybrid between a reluctance motor and a permanent magnet motor.
Okay.
And then there are spoke designs. There are different designs. Spoke is one of the examples which mostly cannot be saturated with external magnetization, because the magnet material is too deep in, and we cannot approach the
in a radial design, right? But not in an actual axial design.
We come to that, yeah. Yeah, I can show you. This will be the saturation line we can achieve. The black line is showing
how deep you can go.
We cannot go deep enough in the radial.
Understand.
Yeah.
So maybe this is a good because you're showing all those FEM or FEA calculations here, or simulations, better to say. This is, I think, also the key competence that Impulse brings into the field of magnetization of rotors, right?
Yeah.
Because you mentioned earlier the if you go ballpark in there and or like just with a rough number, you can say, okay, this is the field strength that I need in order to magnetize the whole thing. But you already mentioned that it's a very high number. A lot, the energy that you need for that goes into the square of this field strength that you need. So the smart idea here that you put forward is you simulate the whole thing. You know exactly the saturation curve. And by having the simulation, by having the physical knowledge about the saturation, you can exactly place the magnetization point of the magnets and know exactly how the magnetization will be later to fit the best economical case for your customer.
We are giving predictions of our results, and they can be 100%, which is nice. If it's cheap and easy to achieve, I would buy. But if it's costing a lot of money, I would also make a compromise and say 99% will do. So this is giving you as an example, but I want to introduce this example. In the current state that we are here in Europe, but also in the Western world, we are now in a situation that we are going local for local more and more after the Corona crisis, but also after the latest political differences we have with USA, but mostly also China. Over 90% of the Earth supply of raw earth magnets is coming from China. And the risk to deal with China is growing and growing.
Okay.
And so we need other supply chains that are freeing us from the dependency of China. So since 90% of the magnets come from China, we have to find other ways to deal with maybe motors without magnets. We come back to the reluctance or the electrically excited motors, which have disadvantages.
So or use less magnets?
We can find a compromise. We make a U shape and we take out these magnets on the side. And we use only a few magnets.
So just a percentage of the magnets that were used. And to fit the large volume, let's say low power density market, this would still be sufficient, I assume.
Yeah, that's a good approach. Well, then still there are magnets and we have to still magnetize them. Some of them may go deeper in now. We can go deeper because we don't saturate the bridges so much. They can be, they can be deeper. But this deep magnet has to be saturated from the outside. So we have to create a tremendous current on the outside to supply sufficient field strength down here. We evaluated and we gave out a map of where is the dark red, where is the light red, and so
on the screen it probably just looks red.
Okay, I can say here is light red, there's dark red. Light red is 99%, dark red is 100%. In average, this will be a saturation of 99.3%. on the 70% line of the knee point.
Okay.
Yeah. So that is what we evaluate and that we can offer to show what can be achieved. So when we design new styles of motors in order to minimize the amount of neodymium, we can go these ways. It is always good to discuss. If someone develops a motor, it's always good to ask back, is it magnetizable or not?
Okay.
I can give you an example of something that is been done, research, which is very nice.
Yeah, research meets reality.
Yeah. This is a real research been done. It's it's been almost the same motor that we've seen here, but it's an improved kind. The researchers have taken out the magnet from here and brought it up there, and they added one here. It's a fancy shape. As a lane, I wouldn't understand why it's better, but it comes out with a higher torque, plus 28% of the torque, and also with a better efficiency of 0.85%.
Yeah, where's the motor efficiency at the moment, to put this in perspective?
In a range of more than 94, 95% is the normal. So if we have losses, let's talk about losses. If we have 5 to 6% losses, and we can take out 0.85%,
that's already decent.
We have a lot of much better performance.
Yes,
it's like 20% of gain. So it's a good idea to do that. Now, if we take a look at the shape of the magnet that we have, we see this magnet might be kind of contradicting the directions that we have. And if we try to magnetize these, we see that in order to saturate the guy in the back here, we have discussed before, we need to pump in a huge field into this depth. In order to do that, we will already magnetize this into this direction. There's no way we cannot shield this magnet from that field we need down there. So we will always
you need a two-step process.
Yeah, this will be magnetized in the wrong direction in the initial state. And something I did not explain previously is these raw earth magnets, neodymium iron boron, they are so-called nucleation magnets. They have a status, we call it a virgin status, after thermal demagnetization. There is a nucleation effect which makes it very easy to magnetize them in the first time. After that, this nucleation is gone and everything is arrested where it is, and we go only along the outer shape of the hysteresis loop.
Okay, so you need a high force, high energy in order to reverse the magnetization, as you explained for this design. The reverse, that's the second step, is important and needed. So you need, this is the first pair of magnets to magnetize
to saturate.
What are these called again?
Conductors.
Conductors. You need two conductors giving the overall magnetization, and then you need smaller conductors specifically targeted at one magnet to reverse its direction.
The goal here is only to reverse this, so we have a strong current right beside, and we need a smaller current which is protecting this guy.
Okay.
So because this may not be reversed also, but we need a stronger field here. We need about 1.5, 1.6 times the HCJ value. Whoever knows something about magnets may know HCJ is the zero cross of the loop through the, after the knee point where the zero cross comes. And we can supply up to 2,200 kiloamps, is something we calculated, inside this magnet.
Okay.
If we divide by 1.6, we come out at a HCJ value of maybe 1,400.
Okay. To show off against competitors. Just kidding.
That is, but this is for many of these magnets not sufficient.
Okay.
So that means it will not be fully magnetizable. Even with this fully strong reverse field, it may not be possible to magnetize this assembly of. So the idea is very good and efficient, but the production process is not possible with a second step magnet, with after assembly magnetization.
Mm-hmm.
Yeah, this shows whatever we change in terms for the reduction of the amount of permanent magnet has to be also taken into account the production process.
Okay,
This
gotcha.
is where we come in.
All right. So let's come out of this physics class a little bit. So I think we understand now what you do is two things, I think. One is understanding the theory of how magnetization of different rare earth materials work, right? In a one-step process, but also if needed in a multiple-step process in order to get the magnetization topology that you need for a particular application in order to meet especially also the economic factors on using less magnets and bringing them to the saturation point where they really can function optimally to exert a maximum amount of force, meaning a maximum amount of torque within the motor. So how would this now work in a machine? So I think this is also the second key competence that you bring. You transfer this knowledge into machines that actually work in industry, correct? Can you explain a little bit on what you do there? And
yeah, of course we have to cope with different physical problems we achieve by the amount of energy that we pump into the magnetizing coil in a very short time.
Yeah, we're talking about kiloamps, right? That is not about amperes.
No.
Like amps can even make sparks,
Yeah.
but we're talking about kiloamps. But of course, at a very short period of time. You mentioned capacitors. So you load capacitors and then you release a lot of energy, channel it through those, I call them electrodes here. You have a different name for them, right?
Conductors.
Conductors. And then through channeling this amount of energy, meaning amps, through them, you create a magnetic field that is magnetizing those magnets.
Due to the amount of current we pump in, we create forces. And these forces you have seen in the lab before. We had 20,000 amps through the two conductors, and they were been pushing away apart by the pulse. These are in a range of 80 kilo, 800 Newton, maybe 700. We are talking about 100 or 200,000 ampere that we pump through maybe axial field strength. We give you the 8-pole demonstrator, and this is something we pump in more than 100,000 ampere, 150,000, around that is the range. And so
you have to withstand the forces within the machine, correct?
It's about like 60 times the forces that we had
in the demo. Yeah.
Sorry. Yeah, it makes a loud bang.
Yes.
So we have to capture these forces and we have to make it elastic because the force is always active. We have ceramic, it will be fragile and brittle and break.
Yes.
So we have to capture the forces. But also we have thermal effects. We have thermal stress that we have to be able to release and to operate in the cycles, to not only withstand 1 or 2 pulses, but like 1 million or 10 million of pulses, because the production rates are such. Yeah.
Okay. And let me think for a second. So so you build the machines, and what is, if you look at the from an entrepreneurial point of view, why should I buy an impulse machine? Like, what is the key competence on machine level that you deliver?
Also basically it's the prediction of the results that we offer you already in the quotation, that gives you right during the design phase of the rotor. A very close cooperation with us can lead to an optimum. The result is close to 100% or even 100%.
Yeah.
And the production ability is given. So this is one of the good points. But also then the question is, what is the physical possibility? We have developed ways to saturate even Halbach arrays in a very deep end
Yeah, you explained me this is some crazy motors that you use for like hypercars, or that you deliver actually the technology for building hypercars, where there's no ferrite in there anymore, but only magnets, correct? And the rotor.
Yeah.
Oh,
There's no return path of steel, and so it's only the magnets. It's in axial motors, and yeah, this hypercar is driven by a very huge axial motor, and yeah, we have developed a very strong coil to magnetize with only one pulse the whole coil, the whole rotor, into saturation. So and yeah, we are doing this with a certain technology that we have. We pump in a very high current through the. I go through the slides here.
Yeah, there you can see an axial motor.
Sorry.
Right?
Yeah, this will be one of the coils for axial motors, and we pump tremendous currents up to 300,000 ampere through those little copper bars. I give you this example, which is also the demonstrator here. And we are pumping more than 100,000 ampere through these strains, and they are creating the flux densities on the surfaces, which are strong enough to saturate. And yeah, the good part on this is we don't use any iron in our magnetizing coil as well. So it's something you just place in by hands, the rotor. You can start the process, and it's no iron anywhere. You can take it by hands. It's
yeah,
no
you can take it out again after magnetization. So if we look at the from an entrepreneur point at the competitor landscape, and the whole campaign, this whole battery expedition is meant to shine light on the competences that we have in Europe. And you also mentioned the supply chain issues, etc. What is the status of your company and the field that you operate in with regard to the global developments? So would you say, like, talking about axial motors, the developments there, the competences that the physics competence that you bring in, is this enough to be sustainable from a business point of view over the long term? Looking at the developments also in the Asian world. I mean, the whole auto industry is built up there right now. How do you see that? To segue over in a little bit more economics and business discussion.
Well, by the technical point of view, I would still say that there is still a gap from here. If we take a look into the American market or the Chinese market, I could say that even though this is a very niche branch, we have very few competitors in Europe, maybe two hands full. That's it. In China, we have more competitors than that, so there are more than here, but only in the last years they grew up. Still, we have solutions they don't have. Like
the other way around, right? In the batteries world, where I come from, we are running behind, basically. Not in all aspects, but in many. And here you're saying it's still the opposite. So Europe is leading the game in this.
Yeah, we have technologies to speed up the production rates. We have technologies to create local higher field on local spots, higher fields. But this is something to set up the electric circuit in the resonance, which is in the oscillation, which is.
I mean, this goes into your IP, into your property, intellectual property that is making Impulse unique in their competence. Okay, understand.
Yeah, but I would still say, I mean, we are working on physics, so physics is available for everybody, for the Chinese, for the American, for us, for our competitors locally in Europe. We are knowing us very well, but we know also our advantages and disadvantages. So I would still say that the European, as general, are really leading technology worldwide in terms of magnetization.
Okay. Yeah. Sounds good. If we look at the developments in e-mobility in general, I think we still have quite some challenges in front of us. And for that, to shine light on this, ask the leaders of our field 3 main questions that I repeatedly ask. And I would also like to ask them to you. From your perspective, what are the main challenges for building up the e-mobility ecosystem with respect to your field, of course?
The supply chain, absolutely. If we talk about the magnets, we have to pick up the fabrication, the recycling of permanent magnets locally here.
Yes.
We are still dependent very much on the Chinese. We won't come out easily, but efforts are taken to build up production lines for recycling. Companies or many institutes have developed processes, but they have to be applied in the field. And then the quality must still fit into where we are. The Chinese are ahead for that.
Okay. Oh, in terms of what?
Also in the recycling of permanent magnet. As far as I'm informed, they disassemble the magnets into raw grade of the elements, while we still use the compounds and assemble them into new. Yeah.
Okay.
So there's some room given that we need to work on.
Okay, so while we are ahead on the engineering part on magnetization of magnets, we are already lagging behind on the recycling part, even though it's for us even more crucial to build up the recycling capabilities here.
And politically, we should find ways that the Chinese don't buy our scrap. Right now, they buy away our scrap for more money.
So we are buying the pristine material, and they're even buying again the recycling material.
A lot of that is happening. If we can keep it here and the scrap that we produce, and we use that as a raw material, and they don't buy it away, that would help us somewhere. But it must be economically.
And I mean, the Chinese are not to blame to do this, because this is economics, right? But we have to build the competences and also to make the entrepreneurial decisions in order to move our industry in that direction, to build the capabilities.
Yeah, it must be the capability, but also a political way to do that.
To put up the barriers or gives the incentives, positively speaking. So positively speaking, what is the potential that we will have a good vision, a shiny one?
We have a huge culture in research still in Europe, and we should take use of that, and we must gain courage and vision to create the full production lines locally.
So final question, what is, if you would have one wish or one advice, what would you give to our industry to move forward to build the European EV or e-mobility ecosystem?
There are many European projects and research which are activated, but we need cooperation Europe-wide. Which has to be again not Germany, not France. We have to cooperate.
On which level? On the political level, on the research level, on industry partnerships? What do you foresee?
I think mostly on the political also we need to do that. But culturally, yes, in terms of language, I still find it culturally not so easy to go cross borders like it would be possible within China, within US. They have it much easier than we are. That is surely still our disadvantage we have in Europe.
All right. So then I think we note down this as homework. And I will try to take this also with me on the battery expedition while visiting many other companies, and spread the message that you also put out now as a partner of this campaign. And Sebastian, thank you very much for this conversation and having me inviting here or visiting.
It's a pleasure being part of your expedition. Thank you for the invitation.